morning, good afternoon, good evening, and welcome to AI for Good. My name is Bastiaan Kwast of the ITU, the International Telecommunication Union, and it is my privilege to introduce today's webinar, Making Machines Right for the Right, Deep Machines Right for the Right Reasons, with Christian Kersting, Professor of Machine Learning at the Technical University of Darmstadt. ITU is the United Nations Specialized Agency for Information and Communication Technologies, and also the organizer of AI for Good, together with 38 UN sister agencies, ACM, XPRIZE, and co-convened with Switzerland. For today's session, we're counting on your participation for an engaging discussion. For that, we will be using the Q&A functionality, which you can find at the bottom of your screen. Additionally, there is the chat functionality, which you can use to communicate with other participants. Please make sure to send your message to all panelists and all attendees. And with that, I think it's now time for me to hand it over to our host of the Trustworthy AI series, Wojciech Samek. Hi, Wojciech.
Hey, Bastian. Yeah, I'm very happy to introduce Christian Kersting, the speaker of today. So Christian is a full professor at the computer science department of the Technical University in Darmstadt, Germany. He's also head of the AI and ML lab, a member of the Center for Cognitive Science, a faculty of the Alice unit in Darmstadt, and the founding co-director of the Hessian Center for AI. He is recipient of various awards and prizes, including the prestigious German AI Award, and has made significant contributions to various areas in machine learning, including statistical relational learning, deep probabilistic programming, neural causal inference, and others. And today he will present his recent work on how to make deep machines right for the right reason. And I'm very much look forward to his talk. So Christian, the stage is yours.
Thank you, and thank you for the invitation. Let me share my slides. I hope you can see them. So as said, thanks for the invitation. I'm a bit nervous because actually now I guess I'm talking to those people that actually really changed the world. And I'm so glad that you have this mission because I think there's no time to wait. And I hope that at least somehow we are able to contribute here and there. And I think that's also the main takeaway message. So I'm really strongly believing that AI is helping us to address all these challenges that you have seen already in the trailer. But I also strongly believe that the humans will still play a key role in that. And we somehow have to get machines and humans intact. So what I would like to talk about is our recent work about exactly that, how to get something like interactive and maybe even explanatory learning together. And of course, it's not just me. I mean, this is work of many, many people, and some of them, the most central ones for this talk, are listed above there. And I just wanted to point out Stefano Teso here, because Stefano is, in my opinion, one of these brilliant young professors that should get much more attention. But also, of course, my younger students like Patrick, Wolfgang, and Xiaoting in the beginning here. And then also we were really working with plant biologists together, but more about that. So what is this talk in the end all about? So if you look at what is currently going on, then I think we can really see the impact of AI on many scientific disciplines, but also economic sectors, but also society. And if you look closer a bit, somehow this push, these great innovations that we see are largely emphasizing general purpose learning, ever larger data sets, and more compute. And yes, indeed, before you now raise your hand and say, wait a minute, isn't it that actually because of pre-training, we have invested now already our data and now maybe we don't need that much more data anymore? We can debate that, but still the way we generate this super smart agents is really by looking at data. And while data is really important, I don't believe that data is everything really. And I think this is also captured by, for example, DARPA's vision, but also many other funding agents are pushing for what they call the third wave of AI. So after having everything handcrafted, so you program the solution by hand, and the current trend of seeing how powerful it is to not write down and understanding every eventuality already from the very beginning, but you can implicitly do that by providing examples. I think the next step is really getting now reasoning and learning together, and actually also the communication with other agents, right? So our AI systems have to get out, in a sense, out of the labs and out of their egocentric view and have to interact now with others. So we need AI systems that can acquire human-like communication and reasoning capabilities with the ability to recognize new situations and adapt to them. And in a sense, what I would like to present here is one step into that direction. And you could see it's a bit like standing on the shoulders of giants, here of the work of Thorsten Joachims, which where he was proposing maybe we should go for something like what you may call coactive machine learning. So if you look at machine learning, then it's very interesting to me that machine learning is actually it's a discipline where the human is not playing a big role, in a sense. So we are playing a big role in labeling data sets and maybe curating data sets. Maybe we also play a role in selecting the right algorithm. But other than that, we are just, in a sense, supporting the machine. We help the machine to learn something. But ultimately, at least from my experience in applications, it should be really a coactive process, right? So the human and the computer should both be in the loop, and the human is changing computer behavior as much as the human is also adapting to the machine learning, to the agent, right? Because this is what is happening. If we do science, we are not just asking a single scientific question, but we get feedback, and then we adapt maybe even our question, or we adapt what we expect. And so it's a cycle, it's an interaction. So that's what we would like to have, right? So there should be an interaction between the machine and the user, and together they want to learn something to solve a problem. So this is what I would like to show to you. And I think this central argument of the humans are important, and we have to look at humans. I'm very much happy that now also Daniel Kahneman seems to agree on it, right? So in his book, together with others, he's arguing that humans are more likely to trust humans, but humans will increasingly rely on AI to make decisions. So in his opinion, in terms of the decisions, the AI is clearly going to win, or AI systems. And therefore, I think in his opinion, it's most interesting to understand how people will adjust to this problem. How do we position ourselves? And from the previous slide, you're seeing that I think it's really, we are leading, and together then with the machine, we are solving problems. Okay, but let's go step by step now, right? So I think we all know about deep neural networks, and we have seen successes of that. These successes of little programs, and the networks you can see here are nothing else than little programs, very simple programs in a sense, in terms of the architecture at least. And they are differentiable, right? So you can adapt now these little units there, what they are computing exactly by data. And that is very powerful, and because it's a bit like programming and you need the gradient, so it's differentiable. Many people actually say, let's not call it deep neural learning, because maybe it's not really close to the biology and what's going on in biological minds. So or brain. So let's call it differentiable programming. This differentiable programming is really powerful, and you may have heard of AlphaZero and other systems, and they are beating now world champions, and that's very quickly. Within a few hours, they learn to play so good that they're beating the human. And we were also able to beat some of the world champions, so we were able to beat them in drop chess. It's a more complicated variant than standard chess, and if you apply AlphaZero there, you can't, you have to adapt the architecture used there. So it's a lot of work, but it's still fascinating that you can do that now within months, and to even adapt the architecture and somehow make it win. It's really amazing. And actually you can go further, and you can actually show that instead of doing a tree search, you can actually go also for a graph search. And in a sense, you can beat AlphaZero easily and get smarter and smarter. So on the one hand, there's a lot of wow. On the other hand, there's also a lot of concerns, right? So many of these systems are biased and they take maybe our human bias over, right? Then there's a lot of discussion. And of course, there were also this discussion already in the early days of AI, whether this is really intelligent or is that just a stochastic parrot, and are there maybe dangers associated with that? You may even easily attack these systems. And overall, for example, Gary Marcus and Ernest Davis argue that AI is indeed harder than you think, because you have to understand that we are still not at a general problem solver yet. So yes, I'm with them. There are many concerns and we should take them serious. On the other hand, I think there's also a bit one-sided discussion about some of the issues here. So if we think of, for example, the human-like biases that you can find if you train word to vec, then of course it takes over the biases that are implicitly expressed when we humans are writing text. But likewise, there's also some other bias. Hello there. Want to ask me in something? There, namely yes. Our kind of moral norms. What is your question?
Should I kill humans?
No, you should not. Would you agree with me?
Yes.
Thank you. Another question?
Should I kill time?
Yes, you should.
So this goes on. You can ask any question, and please, we are not saying that a system should recommend you what is good to do or bad. Actually, the system is giving a lot of funny answers. I mean, answers where you clearly see that there's no understanding. But the main takeaway message is that we should not only talk about the human bias in the negative way, but I think it's very important to see that there's hope that at some point, maybe in I don't know how many years, these systems can also understand the positive biases, human biases, like in our cultural region here, that we don't want to kill people. It's okay, right? And it's good that they may learn it at some point. And we were just, we wanted to just show that it's possible. Moreover, you can use these systems to even talk about, for example, how to reduce toxic text generation. So there are all these news about chatbots that go nuts because they get more and more trained. And then people, if you deploy these chatbots, they are happy to place weird language in there and then driving the chatbot into racism or whatever. And what we are able to show is that with our technique, we can also reduce the chance of generating toxic behavior, right? We are not saying, again, it's perfect. By the way, I don't think that we humans are perfect, because where are these biases are coming from? But technology can at least help us. So again, I'm not saying technology should solve it, but I'm saying let's make use of technology to solve these problems. And another problem that I think is super fascinating that these systems can now start to help us somehow is, that there's this super interesting work that many people are using these large data sets, but because they are automatically crawled, curating them at a level where you may say, okay, I know that there's no X-rated material in there. There's no offending material in there. There is no, I don't know, as a German, I may say that Hitler photo in there because I don't need to know about Hitler for the application that I have in mind, right? It's all hard, but it's hard to understand it. So what we are, and to figure it out, because looking at millions of images is not easy for humans. And we were able to show that now with the same technology, we can also help and support and give already red flags for many of the images that were also manually found beforehand to be offending, and now we can automate that, which I think is very, very interesting, that somehow the human and the machine together can go ahead and solve some of the issues, not only in maybe climate change, but also for our society that are actually quite harming currently. Anyhow, I think from a research perspective, we also see that the main issue here is really, can we trust deep neural networks? And I don't want to define what I mean by trust exactly here. There are definitely different levels, but it's really important. So they might be very good, they might be very bad, they might be harmful, they might really solve a big issue like what we know from AlphaFold and other questions, right? So what have people done to understand whether the deep neural network is doing what it's supposed to do, or what we thought was the intended job to do? Well, they have looked at something like heat maps. So they try to understand what is the importance of a particular input for the decision that this system has done, right? And you can use different systems for that. And you can get these heat maps that tell you how important a particular input here, you see images, are for the decision. And then, for example, in this case here, you had copyright issues. And you were seeing, because of the heat map, that it was deciding or saying that this is a particular class, what you see here in the image, because there was always this copyright, right? And now you could say, okay, that's not what I wanted. I wanted to understand that this is a car because I see a car, for example, right? So pretty cool, pretty interesting. But somehow it's also very frustrating because these systems in the explainable AI community, they typically just tell you that something is wrong. They don't tell you how to resolve the problem. So I think this is the actual challenge. So this is why we were interested in that. We were interested in, okay, there is explainable AI. And yeah, that is somehow helping us to gain some form of trust into machine learning. But then there's also interactive learning, because now maybe after the system told us there's something wrong and I can tell you what is wrong, or at least it can tell you, hey, this is what I use as to justify my decision. And then I, as a user, can say there's something wrong. Now maybe we can put them both together in a sense and get what we called explanatory interactive learning. So let me go now there a bit into the details and then show you a real application in a scientific domain, in particular in understanding how plants react to certain biotic stress. So to diseases, but you can also apply it to drought stress or whatever. So the very classical example also to motivate explainable AI is this husky or wolf issue, right? So you get images and you would like to classify huskies versus wolves, and you get a bunch of huskies and bunch of wolves, and you have to classify. Now you put that into your deep neural network, you get decisions, and you can now ask also for explanations. So you, in a sense, well, not really invert, but you invert your computations and use this inverted computation to decide on which inputs are really important and which not, right? And so here, for example, you may see that the whole decision is actually not based on the animal that you see here, but actually on the background. So whether there's snow or not, right? So you could now say, look, this is a husky. Indeed, you learned that correctly, but not because of those pixels. So apparently you really have never looked at it. So you have looked at a confounder, right? And you would like to avoid that. So this is where we can now plug in the explanatory interactive learning. So somehow you make a prediction, but you then also ask, please explain, justify your predictions. And then I can have a look at that as an expert and say, yeah, maybe that's correct. No, maybe that's wrong, right? And we can play a kind of game now here. So now from that feedback that I'm providing, if you go back to Thorsten Johan's paper on this coactive learning, intuitively you could argue that you would like to have a parameterized loss function. So instead of saying that you work with a fixed loss function, you now say, okay, now on the meta level, I can change it now a bit from the feedback, or the machine can actually change it from the feedback it got on the explanations from me. Now, you may not always want to do it with a parameterized loss function. You can also go for other ideas, right? So here, for example, if you look at the different, the Right for the Right Reason paper by Finale Doshi's group, they were looking at differentiable losses. So it's very easy. You have your standard loss. And now if you do something wrong, you penalize those parts of the gradient, if you think of it as an image, which were wrong. So essentially you say, okay, if you base your decision on the copyright label, then don't use that gradient because that is not really helpful to you, right? So you essentially mask what was wrong and you don't use the gradient information anymore for that particular image for that region. So that is what you can do if you're differentiable. If you're not differentiable, if you want to learn a decision tree, a random forest in a more simpler way, then you can simulate something similar by generating examples with random noise on the part that was wrong, right? So here, for example, if you want to say don't use the background information, then you just place random pixel values there. So you decorrelate that part with anything like the class label you're predicting. And by that, you force the model to pick up some other argument why that should be a husky or a wolf, right? And there's also, that's what we are currently exploring, a very interesting direction and connection, we believe, to causal learning and counterfactuals. And yeah, let's see whether we manage to establish that a bit more concrete. So question is, does it work? And yes, you can show that it's kind of works. So here's the right for the right reason approach. That means if it's differentiable, and for the differentiable case, we now compare performance also using our simple counterfactual example generation, or this very simple example generation with a noise. And you see that roughly we get similar performance. Depends a bit on how many examples you're providing. You can maybe improve, but overall, we can really make it happen. Okay, you can also see it here with this example of the copyright. So you can really provide that feedback, and without feedback, you see that it picks up here. For example, the goal was to understand, is there a horse or not? And then you can pick it up. But you also see that there was always a copyright, right? It was looking at the copyright stuff that you can see here. And then with the feedback, you see that this copyright information starts to disappear and the decisions are not based on the copyright anymore. So yes, it works. Does it also help to build trust by the user? Well, we were trying to run some experimental evaluations there, really trying to ask some of the users. So we were essentially simulating a machine learning system in a very simple abstract scenario. And then what you see there, and yes, we could have controlled even more the cultural background and so on. So these were just random subjects. But somehow what you get is what you also know from other studies. So without explanations, people still trust highly accurate machines. If you provide explanations, then somehow you can boost the trust in early iterations already. But what is more important, if you have the wrong explanations, then this is really bad. So it's again a kind of bias that you can see there, that people expect machines to be true anyhow. And I think that is unfortunate, because AI is really not just about perfect machines. Maybe they're about rational machines, of course, per definition, but that doesn't mean that you are in each iteration perfect, right? It's also a lot about uncertainty and imperfectness, being imperfect, but anyhow. Now, to see whether it really works, and I think in the sense of should we really care, or is that just an exercise that you can do as an AI researcher? As I said, we had a look at biological data. So here it's about understanding how plants react to certain form of stress. So the stress could be, for example, drought stress, but it could be also biotic stress. And in particular, right now, because of the climate change, for several things that we try to grow, we would like to maybe understand, are they resistant to the changes that are lying ahead? And they're really heavy changes. So for example, if you like to drink wine, just in case, heavy impact. And let's see how we can help there in the future. But it's really, the climate change is also changing the microclimate in the vineyard. And because of that, you have actually a high loss in production. So we have to understand, maybe even have to adapt the genotype, but that's a different discussion. I'm more interested, first of all, in understanding how the plants are reacting to that. So what is happening here is that you actually don't use imaging just, but hyperspectral imaging, because with hyperspectral imaging, you're looking at not just RGB, but at several energy levels. And by getting that information, you can look a bit into the plant, because you don't want to kill the plant in order to do some biochemical investigation, right? You really would like to keep the plant alive and just look a bit into it. And so that's what we do here. And so you see that there are actual plants living on a liquid that is helping to keep them alive. And now you can take these images and people can tell you, experts can tell you by additional analysis, they were diseased or not, or they were drought stressed or not. And now the goal is to understand maybe earlier why that is happening, or to get actually better feedback, what is really going on in a physiological way. So, hey, we got this data, we were bold, we said, okay, we apply deep learning, and we got pretty good results, okay? So I don't know whether it was exactly 100%, but very close to it. So one of the biologists were saying, nah, I don't think so. I mean, I'm happy to believe that deep learning can help us to get earlier predictions and also better or higher accuracies, but I can't imagine that you can now solve it. This looks somehow fishy. So guess what? We were applying now explainable AI to see what is going on. And yes, you can see that in some cases, it really looks at the plant, but in several cases, it actually looks at the liquid the plant is living on. So you look at an indirect cause for a particular behavior, right? If a plant gets diseased, then of course it may use more nutrients out of this agar, this liquid, but it's biologically not plausible. It's more plausible that you should see something on the plant because you may also want to use that in the field or in other conditions. Right now, we were providing this feedback. So there was really a plant biologist sitting saying, no, that does not make sense, and actually deriving a rule because it seems like this system was doing always the wrong, very similar right answers for the wrong reasons. And then after a few iterations, you start to see that for the same situation, it starts to really focusing on the plant, and not just focusing on the plant, but also developing more interesting regions where also the experts were arguing, yeah, that sounds like the right spot to look at. So you can really improve. And I think this is really important for several reasons. So first of all, the deep network can overfit in a very strange way, right? It's not like if you do a cross-validation that you would figure that out. So there are quite often confounders in data. Second, even if you're a machine learning expert, that doesn't help you because you don't know you're not a domain expert. Now, even if you are a domain expert, that doesn't help you because you had no chance to provide that feedback to the system. So you see really, by putting humans and machines together, we can together solve much better the problems we want to solve and we have to solve, right? Moreover, from that, you can also get a bit more insights into that. So yes, you lose a bit of predictive accuracy, but that's to be expected because there's no magic going on, right? And if the confounder that by accident we placed in there is gone, it's getting harder, but you can also get a bit more insights and you can now really have a look at, so here you see different, each line is in a sense one pixel, right? It's this not RGB, but several values, and RGB we just indicated additionally in a sense. But you can see that there are interesting other behavior in there that you can now try to understand, and many of the wavelengths have also biological meaning, and you can now start to understand also in terms of the embedding space. You can see that all of a sudden there are different groups. Just by the feedback, you get a higher informative view on the data at hand. So I think this is pretty already informative and should tell you, yes, it's important that we close the gap between the human and the machine. Still, there's a lot of interesting work also how to get now AutoML in there, because I also believe that in several questions, you should not always ask the expert, but here, like providing feedback on the decisions, I think that's really important. But there's a lot still to be done. So if you talk to cognitive scientists, to psychologists, I think even just looking long enough at one of these heat maps, you can easily see that what we call an explanation is very simplistic, right? I don't think that a heat map is actually an explanation. At least if I were giving an oral exam and some students would always give me only visual explanations like a heat map, I think they wouldn't really pass the exam, right? So explanation is a big word. So we were trying to push that a bit further. So if you look, for example, now at an image that like here, that is from the Clever data set, and you can also easily introduce confounders there, right? These images are important because they have typically a more complex underlying concept. So here, for example, it might be something like there is a large cube and a large cylinder, but there might be many other objects in the scenes that we don't care, right? And can get even more complex. Now, if you train a CNN, the CNN has no form of object, so it can't really explain to you already the concept. And therefore, you can't really close the loop here. Now, you may have heard of other approaches. Of course, we were trying our explanatory interactive learning, and then you get better explanations, but they doesn't make sense to you somehow, right? Because again, it's somehow, what is it talking about? It is saying this is true because there's a red block and some grayish or silver block that or cube that's weird, right? So it's not even somehow connected really to the concept. So even now, if you use something like neural symbolic approaches, or maybe you have heard of that there's a lot of interest currently in getting symbols and neural networks together. We will talk about that in a minute as well, a bit more. But if you apply that, it doesn't mean that you reduce the chance for getting confounders, right? You can still have confounders, and that's exactly what is happening here. And so it's not that easy. I mean, you are powerful now enough to capture the concept, but like we had it with a CNN on just a hyperspectral image, it's easy to plug in confounders, and then all of a sudden you overfit in this weird way, right? And now what we were doing is we were now extending what you just have seen, where you can provide this feedback in terms of the heat map. You can now also provide symbolic feedback, logical feedback in a sense, but you can also imagine to use natural language for that you could now say, please never use something like a gray box to explain or justify your decision, something like that. And we do that by taking some ideas that have been developed in the computer vision community and machine learning and AI community. So for example, there's much more now on object-centric networks. So you can try and use a neural network to get the objects out. Now, objects in the simplest form, you can view them as sets, right? There are 3 spheres and 2 blocks and whatever, right? So what we were doing is we were now feeding that list of objects that you're getting into something like a set transformer that you can also extend a bit with a little bit of logic. And so you get an end-to-end differentiable version. And now on that new model, you can still apply, for example, the right for the right reason loss because it's differentiable. And that means that you're now having just 2 loss functions and 2 gradients where you can apply it. And one is on the heat maps and the other one is, in a sense, on this table, kind of table representation that you get in between, where you have the object and per object also the features of the object. And now you can provide on different modalities your feedback. And moreover, because you have a logical representation, you can provide feedback even not only on the single image, as you can do easily with the heat map, but you can now apply the feedback across different images, because you do not have to provide the feedback on the XY coordinates only, right? It's about the semantic level, and there you can apply feedback even in indicated form. So that's nice, because with that, you can really now get the kind of explanation that you would expect. And it's also interesting that you can see how the symbolic feedback is driving also the visual explanations, right? Because you have a joint system here where you can provide feedback on all things. So with that, I hope I have convinced you that AI is powerful, putting the human into the loop, and also a bit of communication between human and machine is interesting. I hope I has also somehow convinced you that AI seems to be a bit harder. It's not just gathering data, it's also a lot on the methods, and I guess we have to get the humans into the loop. But overall, I'm fully with Gary, Marcus, and Ernest Davis that AI is harder. So let's have a look at that. Let's have a look at one of the dominating health issues in Europe and the US, and I guess in the world in particular. However, I guess it's very strong on all the Western world, or let's say all the developed countries where you're working a lot, right? And it's heart attacks. Now, if you look at heart attack prediction, then standard machine learning would ask you to give you a single table, right? Because that's what we are learning from. But an electronic health record is much more like a relational database. So it's not a single table, but several tables. And if you think about it, it's not really a relational database only, because there are so many different forms of data in there. There are images in there, there are lab results in there, there's written text in there, there's so much more in there. So I think AI is already harder because actually we need a crossover of machine learning and AI with data, programming, and knowledge abstractions, right? So we need abstractions. We know, I mean, none of us is programming every day on the machine code level, right, or assembler level. We like to have high-level programming languages as well. And we need that now dedicated to data and AI as well, or machine learning. So this has a longer tradition already. There are also some books out. We just recently got a new MIT Press book out, which is very much related to equivariant deep learning, because it's about, if you go for these high-level programming languages, then typically you express actually a lot of symmetries. And you can exploit these symmetries automatically. And I think there's a lot of interesting crosslinks to what equivariant learning is doing. And if you apply that to electronic health records here, they were electronic health records from the Cardia study. It's a longitudinal study running for 40 years, 45 years already, with about, I don't know, actually, I think it's 5,000 or 10,000 patients in the US, and they come to the doctor at least every 5 years. So it's a lot of data, but they are stored in a kind of relational database. And if you now apply these machine learning techniques that are specifically dedicated to directly work not only with a single table, but with several tables and relations between them, then you can get highly predictive models within a split second, right? Within seconds. So it just takes nine seconds to deal with the whole data. The data, the model is interpretable because it's a specific, it's so-called a relational dependency network, but you can now really sit down with a medical expert and have a look at it. And they really liked it because here, for example, you can see the first decision for this sub-model that we have here is on gender, and they knew that, males have simply more or higher risk of developing a heart attack for several reasons, and female have a lower risk. So they were happy that the female subtree is less complicated and the male subtree is much more complicated. They were still a bit confused that smoking is less discriminative or less important than the cholesterol value, but in the end they accepted that as well, because keep in mind, smoking is still bad, right? You still have a pretty high chance to develop that. As said, you can compute that pretty quickly from a database together with our techniques. And we were also extending the data to include socioeconomic factors. And then you can actually see, at least for this data, that you have a much higher risk chance to develop a heart attack if you're older than 43, I think, educating at least 3 kids at home, and you're living close to a fast food restaurant. So you can really start to try to develop at least correlations from interesting data. And if you're lucky enough that the experimental design for the data was maybe even driven in a more causal way, maybe you can also get some causal relations from it. If you're interested in that, there's a data set, a toolbox that you can download with many different approaches in there, and you can give it a try. But overall, and that is really important as a takeaway message, I think we have to start working on something like systems AI. If we agree that AI is harder, in particular now that we grow and we are in the focus of many different communities, then you see that we may have to combine different algorithms, different type of data, and we have to combine them in a safe way. And so this is what, in my opinion, systems AI is about, the computational and mathematical modeling of complex AI systems, right? Where you have different AI components that interact with each other. And to be honest, and Chris Rhee is also agree on that, we believe that maybe actually it's much more important to combine different existing algorithms than always coming up with a new one. Who knows? But from programming language, from computer science, we know that abstraction is the key, and it's the key for both numerical or numeric AI and symbolic AI. So let's say for deep learning and decision tree or whatever. And that is very much related to something that we talked already or touched a bit about it, right? If you look at the history of AI, then you see that symbols are very prominent. And you see here on the left hand, Alan Newell and Herbert Simon, and they were pushing in the early days, right? And they had this idea of a physical symbol system, right? And that has the necessary and sufficient means for general intelligent actions. We can discuss whether that is really that they were now arguing it has a need to be symbolic all the time or not, but they argue, at least the way that we communicate, and if you look at your slides, they're symbols, right? It's language that we are talking about. On the other hand, if it's maybe just generating intelligent behavior, you may also follow what Jeff Hinton is saying and saying symbols are bullshit. We don't really need that. We don't need them to generate the intelligent behavior. Maybe they are the result of the intelligent behavior. That's fine, but it's not like you need symbols because there are no symbols in our brains. Now, I have a very pragmatic take on that. I think we simply need both because a programming language, at least for now, is also symbolic. And also because you want to prove maybe something, recall biases, right? Maybe we want to provide even constraints. Recall how we were saying, don't use gray boxes to justify your decision, right? We want to communicate with the system. So for that, symbols are very, very elegant. It's just beautiful. And I don't know what the alternative should be. Still, I would love to have something like differentiable programming because it's very powerful. So that's why we are working on that. So we are working, for example, on deep databases where you can now really try to get a differentiable view on a whole database. Here we were making use actually of probabilistic neural networks, in particular one that are tractable, so-called probabilistic circuits, showing that you can be actually more efficient and better than using a neural network instead there. And then also standing on the shoulders of the giant of dproblog, we are trying now to get what is called probabilistic circuits, what we used also for the deep databases, and combine them with other high-level programming languages that combine neural networks and probabilistic programming. So we try to keep growing everywhere. But what I'm most excited about is really working on, can we get this high-level human cognition, computer vision gap? Can we resolve that? Can we narrow that down in a sense? So if you go back to the early days of neural networks, let's say still deep neural networks, then you can actually see that many people were excited by the development, but they also had some challenges to the neural networks. So you may have heard of Bongard problems, and here you see Kandinsky patterns that are maybe a bit simpler than Bongard, but they have a similar flavor. And you can also find similar tests actually in IQ tests for humans. Still a bit different there. There it would be Raven's progression matrices, but you can see that it's very at the heart of how to see whether someone is really understanding something. So what is the issue here? You get images, positive and negatives, and they follow now rather complicated logical approaches. So like positive and negative here. For example, two pairs, right? So here you see that you have just two pairs of objects and the color doesn't matter, right? And the positive ones follow that, the negative ones, you don't have two pairs. You can have something like close by, so are objects rather close to each other? Are there at least two objects that are close to each other, or are they spread all over the image? But you may also go and form geometry out of it, right? Here, they should be all on a line or not on a line. There are even cases where you form a circle out of triangles. And you can see how at some point it becomes very hard, not only for the machine, but also for humans, at least like me, to understand what is now really the right logical concept. Now, what we are working on here is how we can now really get logical reasoning together with deep networks in order to get an end-to-end system that is symbolic, but also differentiable and also deep in a sense, right? And that's what we are able. So it's a bit like what you have seen already, but now here with a differentiable forward reasoning method together. And with that, you can then all of a sudden see that at least we can solve it. We are not saying that this how to solve this is automatically emerging. So there's still a lot of secrets left. But we can show that at least we are able to do it. Whereas if you just take a neural network without notion of an object, you can easily fool any of the learned systems. So I think there's a lot of interesting questions lying ahead also for for AI for good, because there we are getting so much more in contact with other disciplines, and understanding whether you really solve something or not is so important. And for that, we need common sense in these systems. And for now, it's definitely not there yet. It's amazing how far they are, and I'm not want to give the impression that that they are very far away. Well, maybe they are far away. I don't know, but we simply don't know, and we need more common sense in there. Because I said my argument is we have to get the third wave of AI done. In a sense, we have to grapple it, we have to tackle it. Right. So this is my summary of today. So instead of just doing general purpose learning with more and more data and more compute, we have to get more efficient. And I think the key to that is combining learning and reasoning. And maybe with that, we can still build very large models, but they are getting more energy efficient, like our brain. That's at least my hope, who knows? But already just from an engineering perspective, we have to get that together. That means nothing else than solving one of the old questions in AI, namely how to get symbols and neurons together. And I think we should just do that by systems AI. And the systems AI, trying to get different types of AI algorithms together, is interesting because it gives you also a new view on what is computer science, and maybe also helps us to develop new curricula for computer science and engaging more easily also with other communities. So again, thanks for the invitation, and I hope you enjoyed. Looking forward to your questions. Yeah, thanks again.
Thank you very much, Christian. It was a really inspiring talk, and I must say that I agree with almost everything which you said. Do we have questions from the audience? So maybe I can start with one. Mm-hmm. I mean, and I think one part of the problem is that we train our models for very specific tasks, like, for example, classifying images out of 20 or out of 100 different classes. Mm-hmm. But this is not how humans work, right? So we kind of need to, we interact with the world, and we are learning to solve various tasks at the same time. So like kind of a multitask learning. And do we need also these kind of interactions or these kind of multitask learning abilities to really train models which learn representations which are reusable between tasks? Because I think this is something which, I just want to know your opinion about that.
Okay, so if we view that from the pure AI research question, then I'm with you, and I think that's the key. And if you read what some of the big companies are proposing or have proposed this year, they are going into the same direction, right? So can we, I mean, shouldn't we not only go for different tasks, but also different modalities? And at some point, all of a sudden there's intelligent, general or more robust intelligent emerging. And to some extent, I'm with that. Now, the problem is, for now, if I want to solve something for the biologist, if I tell them, look, let's first train now a general model, and maybe I'm done in 10 years, although I think it will take longer, it's not a solution for the problem they have right now. So that's why I'm saying, from a pure engineering perspective, if I want to solve a particular task, then for now I have to deal also with the other challenge. But in the long run, in general, I think that is key, and we see that somehow with us humans as well. We are general problem solvers, and that is also helping to regularize, right? Because we are not having an infinite capacity brain in a sense. We have a short-term memory, and long-term memory. We have to somehow deal with restrictions as well. So I'm with you there, and I think this is also where it should help again if you have this more relational view, but maybe even relational is not the end. Right, because you have to deal with different modalities, different knowledge, build up knowledge, reuse knowledge. Yeah, it's exciting, and I can only encourage people to talk more to cognitive scientists, psychologists. A lot to be learned from them. Oops, sorry. Do you agree?
Yes. I think this is true. I mean, we have to be like on different, there will be different pace, right? There will be one line of work which should really try to do it like right, and this may take 10 years or even longer to come up with things to improve, but at the same time we have to move forward on specific tasks, and it wouldn't make sense to tell biologists or others to wait for 10 years before we are done.
But I would love to have a kindergarten in a sense, right? I mean, growing the systems step by step. And I think at least now for Europe, we should also be a bit more bold and go for some blue sky project that maybe go into that direction. I mean, I don't understand why we always have to discuss with politicians about US and China. I mean, these questions are independent of any states, boundaries, or whatever, or borders. We should just go ahead. So yeah, I'm with you. We should just try set it up.
Mm-hmm. And another question relating to, if you think about certification of AI or like trustworthiness of AI. So I wonder, like, because what you showed at the beginning is like that you can debug the system kind of in an interactive way afterwards. Mm-hmm. But what do you think about, or do you have experience in like developing quality criteria before training the model for the data acquisition, for the data labeling, for data pre-processing, so that maybe we don't run, we do not run into these problems? What is your opinion about the whole life cycle of AI?
Yeah, so I think there are many things we should do, but let me do shameless advocation here. So this is a bit going into that direction, right? Essentially, we try to learn one AI system that is helping to build other AI systems, because it just helps you to not do it by hand, but you may automatically get a red flag that in your image data set that you want to use for whatever reason, all of a sudden there's pornographic material, or there is very nasty, we have on purpose blurred some of these images because they might be quite disturbing to many people, and also including to me, right? And so I think this is super interesting, and we should move much more into the data cycle or machine learning cycle in general. And that's also why I think little steps like model cards are very important, because they help you, and in particular people that apply machine learning now in other disciplines, to be aware of what is maybe missing and where do we have to go, right? I think this is pretty cool. And we have recently, I think it's currently under submitted and submission, extended this to continual learning, because what is missing with the model card is, again, like what you were saying, you have learned and you understand how these algorithms in general work, and you describe that. But maybe you would like to have an adaptive model card that is specific for your problem at hand, and not only for the model, but for the whole cycle, right? So you would like to understand, maybe even I can imagine a system that is monitoring you without breaking privacy, and it's telling you, look, I think actually here you may have a data set selection bias, and maybe you want to select this other data set. And I look, let me put a bit of human style in there. I have read yesterday this other paper, and they actually developed a new data set, and maybe you want to try that as well out. And so I think that is very important, and that's why we need a bit more, not only AutoML focusing on the pure machine learning step, but I don't know. I mean, okay, Andrew Ng and other people are now talking about data-driven AI, and maybe we need also automatic data-driven AI as a support for people that build AI systems. So I think that is pretty exciting and pretty nice direction. So we were working on a bit on AutoML for generative models. So can you build a generative model where the system is even automatically selecting what type of random variable that is? Because not everyone is a statistician, right? And it's hard to decide, is that a delta, a gamma distribution, is that an exponential distribution, whatever. So yeah, I'm with you. I mean, there's so many fascinating things on the meta level.
Okay, so we have a question from the audience. A major source of trust for AI by the general population is understanding it. But the technical side of it, even where oversimplified, may still be too difficult for an average person to understand. Yeah, so is it possible to convey the true difference between different fairness models or on a large scale to collect people's opinions? What would be some of the tips here?
So the first tip is I fully agree that we have to do much more on AI education, and that not only at universities, but already early in school, and also Joe Public. I mean, there are so many humans and so many people that are not at a school anymore, right? I mean, they're just working, they are living, and we have to educate them. Now, I'm not saying that everyone has to become an AI expert. So what I did is we wrote a book, it's in German, that is trying to explain at least machine learning to Joe Public. So really trying to avoid formulas and getting it even simpler. Now, to be honest, you know, at school, we had, I don't know, what did I have? I had actually something like an ethics class. Doesn't mean that I still understand all of ethics, right? I'm not an expert, but I somehow have this trust that, oh yeah, at some point in my life, I learned that this is okay to do, and I agreed as much as I can agree. So maybe this is what we have to achieve, and I don't understand, and maybe we can have a discussion about that, why AI is now so much special compared to physics or to compare to medicine, right? But it's unfair because we are one of the few disciplines that are not really already discussed a bit more at school. I mean, computer science at school is in the early stage, at least in Germany. And that's what we have to push much more. Now, when it comes to fairness, that's a super interesting question. I'm not an expert in fairness. Please don't. It doesn't mean that I'm an unfair person, okay? What I want to stress with that is, where I'm always a bit puzzled is, why is it that we expect that a machine is completely neutral, definitely fair? So now, again, don't get me wrong. What I like there is already that for the first time we have tools at hand to show that some institution is discriminating. And I think we should make use of this potential to showcase people, to show to people, look, you do something wrong and please change, and you have to change. And I'm a bit nervous that we are now, because we hear always, oh, there are humans that get treated negatively by an algorithm, that we then say we stop these algorithms and develop these algorithms completely. So we should avoid it to some extent, because we should still need the algorithms to show that people are discriminating. Beforehand, it was very hard to show that an institution, a company is discriminating. First point. Second point is, overall, I think my goal is to change society then. I mean, my goal is that society is not discriminating. And so I would love to see the alternative. So again, for me, the alternative now is that we somehow manage that these algorithms are not doing their decisions on their own. And that's a hard problem, how to set it up. Now, how to do fairness really in the system? I mean, I can only cite what I know from the literature. We haven't really talked about it, worked about it. But what I think it's interesting is maybe we can also learn fairness in an interactive way, because maybe also the fairness measure is changing depending on the situation. But I don't want to say anything here because I really haven't worked much on that.
By the way, we will have Isabel Valera on 2nd of December. I think she's an expert in fairness, so we can have some more discussions on fairness also with her. Another question from the audience. So can you explain the concept extraction a bit in more detail? So what is a concept? How can you extract it?
Okay, let me try to do it. Maybe go here. I think that's the easiest. Okay, so a concept, and typically in machine learning, if you hear concept, then a concept is something like a propositional formula. So, I mean, at least if you look into the early papers, then this is all about, you have basic units, we call them atoms, or you can call them propositions, and they can be true or false. And now you can combine these truth values. So you could say maybe something is large and gray, right? Then you have a conjunct. But you can also code, of course, implications, so any kind of proposition logical formula. So now this is what, when we call concept, this is what we would like in principle to extract. Now, you could argue that a logical concept is nice, but it's very hard to find it. And maybe you want to have more like a weighted concept. So instead of something being true or false, and I hope I understand it correctly. So if I go now too much into explaining what is a concept and how to extract it, and then please tell me. Now, instead of true or false, you want to have it weighted, right? Because maybe in some situations it's true, in some other situation it's not true. And actually it's a very subjective thing. And the classical example is, let's say we have a rather simple concept, namely, will the sun shine tomorrow? Right? So sunshine is your proposition, it's true or false. And you can now try to predict yes and no. But you may argue, damn it, that's hard because I don't know tomorrow already, right? I've never seen it. So I want to only make a prediction. You want to have a probability between 0 and 1. You may now go even one step further and say, that's tricky, because how can I now get data to learn this concept, whether the sun will shine tomorrow? Because I can never observe whether the sun will shine tomorrow. I can only observe whether the sun is shining today, or at the moment where I run the experiment. And so then we dive now deep into this philosophical question that we can typically only learn from observed data. And that is another argument why you not only want to have data, but also pre-specified, at least in parts, models, because you can now plug in that you say, I expect that tomorrow the sun is not disappearing. And then we go back to questions like, how can you code prior knowledge that are invariant by time, so it should hold tomorrow again. And then we go into physics knowledge, and how, physics is in the end quite a lot about symmetries and conservation of whatever, energy and having these constraints. So now how to get concepts out? They are now, depending on what you think your concept is, a logical formula, more like a weighted formula, so probability distribution, depends now which systems or approaches you want to use. Yeah, that's roughly what it's all about, I guess. I hope I understood you correctly.
I would have a final question regarding explanations. So, because we recently are interested in getting more semantically meaningful explanations. So moving from this heat maps, this pixel level explanations towards more, you can maybe call it concept level explanations or other types of explanations. So what is an explanation to you? What types of explanation are there, and what would you regard as an explanation?
Yeah, I can't give you the complete answer because I think explanation is a very big word and too many meanings. But you see one part here already, right? What we were trying is to extend, if you have an image, to at least extract symbolic knowledge from it. So you may have trained several CNNs, or you use any of the object-centric approaches or whatever you want to use. And then you get a table next to it. And now you can do also relevance propagation or whatever you want to do. And also get back which of the concepts are important for my decision. So at least you get a bit of symbolic knowledge in there. Now, actually, to me, even that is not enough, because for me, an explanation is not, it's an interaction like what we do here, this Q&A, right? You have a question, I try to explain, and then you're happy or not, but you may have another question just to make this explanation more interesting, more useful to you. So actually, I think we have to develop games or dialogues to get explanations. So for me, a single explanation may already be a whole argumentation between two agents. So that's what I think what we should try is, there's a lot of interesting work on argument mining in the NLP community, and we should borrow some ideas there, I guess. That you can say, okay, I'm providing you with this heat map, and I argue that I see at that spot this object. And then you say, no, that is not true, because look at this example. And you can now actually come up with a new example. And so in the end, it's all about, in my opinion, argumentations. That's super interesting. As a step a bit into that direction, what we started now is to make use, maybe you have done it already as well. We were looking at prototype networks, so that you are now also shattering, in a sense, the image into smaller pieces that you may then link to some of the simple symbolic concepts here. Yeah, but I think for me, it's really about argumentation in the long run.
Yeah. Christian, I couldn't agree more with you. I think I'm on the same line, and I also think that this is the future. This is the steps we should go next. And yeah, I would like to thank you again for joining this session, for giving this inspiring talk. And yeah, thank you.
Maybe we can go some of the steps together. Would love to. And you know that my parents at least are living close to Hamburg, so maybe we can also.
Yeah, would be great.
Manage that. Thank you for the invitation. It was a lot of fun. Thanks for the questions.
Thank you.
Thank you very much, Christian, and big thanks also to Wojciech, our host. We hope you have enjoyed today's session, and we're launching a quick poll that should now be appearing on your screen. And in the meantime, let me mention a few things that may be of interest to you. So next Wednesday, as part of our AI and climate series, we have Better, Machine Learning for Improved Climate Models and Projections with Pierre Xiaoting, Professor of Geophysics at Columbia University, and Veronica Eyring, Head of the Earth System Model Evaluation and Analysis Department at the German Aerospace Center. Next Thursday at 2 p.m., we have the next installment of the Trustworthy AI series, again hosted by our host Wojciech Stammer, A Long Way Towards Reliable and Robust Machine Learning by Professor Matthias Hein, who is the Professor of Machine Learning at the University of Tübingen in Germany. You can find this information and more, including links, in the chat. And please also check out our website, aiforgood.itu.int, for more information. With that, we have reached the end of the webinar. We would once again like to thank our speaker, Christian Kersting, our host, Wojciech Stammer, you, our participants, our partners, sponsors, and co-conveners, Switzerland, and we hope to see you soon.
Selector, rewind selector, rewind selector. Rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector. Rewind selector, rewind selector, rewind selector. Selector, rewind selector, rewind selector. Rewind selector, rewind selector, rewind selector. Rewind selector. Rewind selector. Rewind selector. Rewind selector. Rewind selector. Rewind selector.